Hello everyone, and welcome to the continuation of the lectures in the finite element method, in which we are going to basically explain the finite element method based on a book by Daryl and Logan called The First Course in the Finite Element Method. Today we are going to continue talking about chapter 3. And in today's video we're going to be talking about the transformation matrix, the stiffness matrix in 2D, and stress calculations. For the rest of those would be a third part in which we're going to be explaining those three. So sit back, relax, and enjoy the show. Alright, so first things first, we're going to talk about the transformation matrix. Now, what is a transformation matrix? A transformation matrix is basically a cool way of saying cosine and sines. That's all there is. It basically transforms a vector from one coordinate system to the other. Now, the vector transformation is given in the book Daryl and Logan, a first course in the finite element method, but the drawing itself is a little bit cryptic, so allow me to explain this for you. Assume that you have a bar oriented randomly in space, any bar, from 1 to 2. And let's say that the edge point, point 2, has moved a certain movement in the direction x, which we call u this time. Like the movement in the x-axis we call u, and the movement in the y-axis we call v. So it moves an arbitrary value in u and another arbitrary value in v, which gives you a displacement vector d. Obviously, you know that from the previous lecture, which I will link above on the top right side. We know that the stiffness matrix has to do with something called the local displacements, because the forces in the truss are connected to the extension of the truss, because delta equals PL over AE, which gives you that P equals AE over L multiplied by delta. But of course, it was a little bit more it was a little bit more expanded, because you had F1x local, F2x local equals AE over L multiplied by 1 minus 1 minus 1, 1. So we've explained that before, which ultimately meaning that we need the amount of extension and contraction in the local coordinate system. Now, the local coordinate system is the system parallel to the bar. And it is exactly this u that I need, which can be calculated from both u in the global and v in the global. So I'm basically interested in this vector in red, this u prime or dash or whatever, this local u. And you can see that we have a global u and we have a global v. Those two things are global u and global v. Now, because there is an overload of lines, just think about this. Maybe you want to rewind right now just to get your bearings now. This is basically, this crazy line stuff is basically the simplified line stuff, because not everything is needed here. So what do you know? What you usually know is the orientation. This is a given. The orientation of the bar, theta, should be given to you. You should know this. And if you know u and v in the global sense, then you can find u prime and v prime in the local sense, and vice versa. Also notice that in this lecture, we are gonna put a little prime here for everything that is local. For example, if I put f with a prime, then this is local f. If I put u with a prime, then this is local u. If I put k with a prime, this is the local stiffness matrix, because now we have to differentiate. So today I'm going to focus on how to find u dash from u and v. And if you know this, you can also vice versa this entire process. Now, to do this, I'm going to color me two triangles. So look at this triangle that I'm going to hatch now. Now, you can notice that u dash comprises of two pieces. This piece, which I'm now squiggling, plus this piece, which I'm now basically lining up. So I would say that u dash equals OD, as you can see from the triangle that is hatched, plus DC, that I still have not hatched anything yet. Okay. Now, what is OD? From the triangle, this is a right angled triangle. So how do you find OD? Think about it. You might, by the way, this might be confusing, so you might need to pause the video or need to rewind it. This is totally normal. And if you check the triangle OAD, then you can basically deduce that cosine theta will equal OD over u, which means that OD in this case equals cosine theta multiplied by u. That's the first piece. Now we need to talk about DC, the second piece. For the second piece, you need to understand first that DC in green and AE in green are equal. So DC basically equals your AE. So if you know what AE is, then you know what DC is. Now AE happens to be in the triangle AEB, as you can see here. That's your triangle AEB. So if you go and check out AEB, you will get a right angle triangle, as you can see here, and your sine theta equals AE over V, which means that your AE equals V sine theta, which ultimately means if you plug in this into the equation and this into the equation, ultimately this means that U dash or prime, whatever, equals U cosine theta plus V sine theta. This is only for you. Now you can open Dario's book and try and understand how V comes into play. And I hope this is clear. Feel free to ask me any question in the comment section if you need. This is one of the things that you need to basically bend your mind around. Your local U equals global U cosine theta plus global V sine theta. And your local V dash equals negative U sine theta plus V cosine theta after this derivation. You can rewrite this into matrix form by saying U equals cosine multiplied by U plus sine multiplied by V, and V dash equals negative sine multiplied by U plus cosine multiplied by V. The matrix form is a compact way of writing those equations. C stands for cosine, S stands for sine. This is very important because our idea is to convert global stuff into local stuff and vice versa, but most likely global into local. So basically, this matrix or a modification of it is going to be used to convert global systems into local systems. But why? Why are we going to do this? Because we always, in the finite element method, we always going to have an easy access to forces local equals local stiffness matrix multiplied by movements or deformations local. This is easy. We always have access to it because it's called the finite element method with special emphasis on the element, meaning that the stiffness matrix is always derived with respect to the local axes of the element. Now in reality we have global stuff, so we need to basically try to get the global stuff and fit it back into the local and vice versa, by the way. I will show you how this works, which means now in the end, ultimately, that the global deformations multiplied by something called a transformation matrix gives you the local displacements. And D here is your global U and V. D dash here is your local U and V. And T is called cosine sine matrix. So basically what I'm trying to say is that from now local will have this little dash. With that being said, this equation, as I said, is the local equation. We use it because finding K in the local sense is easy. And we know from the previous lecture that this is the equilibrium equation for a local element in which this particular piece is your stiffness matrix. Now the idea behind this is, well, our target is to start with our local system and somehow get to our global system in which I have F1x without this dash. So without a dash, this is global. F1y, F2x, F2y equals KU1, V1, U2, V2. Now somebody would call foul and tell me, wait a minute, you have y forces here. But I thought you don't need the y forces. Wait for it, I'll come to that. Generally, any u in the local u dash will equal global u cosine, global v sine. So of course, if you have u1, then this equals cosine global u1 plus sine global v1. And if you have local u2, this will equal cosine global u2 and sine global v2. With that being said, you get an expanded transformation matrix, but that's not the real transformation matrix for reasons I will talk in a moment. Because I said before that a point could move globally in the x with a movement called u, and globally in the y with a movement called v, causing an extension of the element. But those movements we don't care about. What we care about is any extension in the direction of the bar. So yes, edge points could have movements in global X and have movements in global Y, both edge points. But those movements mean nothing to me. What means something to me is the movement in the local axis for the first point and the movement in the local axis for the second point. And to be able to arrive at those, I need the transformation matrix. Now, to understand this, you can see that U1 equals cosine, U1 local equals cosine U1 global plus sine V1 global plus 0 U2 plus 0 V2, because U2 and V2 do not affect U local 1. And vice versa, the local displacement U2 or U-2 has nothing to do with the global displacements at 1, but has everything to do with the global displacements at 2. So basically, in short form, your local displacements equal a transformation matrix by the global displacements. But that's, however, not enough. Why is it not enough? We have now our transformation for the U. This is like D dash equals transformation star D. In a very similar fashion, you can arrive at local forces equals transformation multiplied by global forces. Because once again, you might have an element that is inclined with a huge force in X and a negative force in Y, for example, so F1 or F2X and F so on. But it doesn't matter, because those forces mean nothing to me. What means something to me is the component of those forces along the local axis. So F2-X, and of course I have here F1-X or something. So in other words, you need the local forces, and to find the local forces, you need to transform your global forces in a very similar fashion. F1X equal in the local equals cosine X global sine Y global plus 0 for the forces in the other node, because F1X doesn't feel anything about the second node in terms of forces. What about F2X? F2X has zeros in the beginning because, well, it's F2X global cosine, not F1X. So because it has nothing to do with F1X, it gets a 0 here. It has nothing to do with F1Y, so it gets a 0 here. It's cosine F2X in the global, so you get a C here. And it's sine F2Y in the global, so you get an S here. This is copy-paste. But now the idea remains here. We have this. Our local stiffness matrix is something we have, and we know immediately it's AE over L, 1 minus 1 minus 1, 1 from last video lecture. However, I don't know what the stiffness matrix is in the global sense. An element, this is one piece of element, and this is another element, let's say, and this is a third element. Now, each element has a local stiffness matrix. So, for example, K-1 is the local stiffness matrix for element number 1. Now, K small 1 is the global stiffness matrix, but not for the full structure. No, for the element. Finally, K capital is the global stiffness matrix of the full structure. So this is our mission. We want to find this. I cannot find this without knowing the global stiffness matrix of the element. And I cannot find that without transforming the local into the global. You would think, but doctor, we have not done this last time. We haven't done this last time because our questions were done or were formulated in such a way that the global x-axis and the local x-axis coincide. They were parallel. However, today it's not going to be the case. So I start with this. And now, what can I replace F local with? I can replace F local by saying transformation F global. So I can replace F local by converting into F global by multiplying by transformation matrix. And I can replace D local by multiplying by the transformation matrix into D global, which means that I am getting one step closer to writing F equals K D. But you can see that I need to do an intermediate step here, because I have T dash or T star here and T star here. It seems that I have to left multiply by the inverse of this. Like if I somehow can left multiply by the inverse of this, then I would have F equals the inverse of T star multiplied by K local multiplied by T star D. And you can see that this is my global matrix K. So this is basically mission complete, because the only thing I need to do now is to invert this matrix. But wait a minute, I'm saying K equals T star inverse K local T. But wait a minute, I cannot invert this, because for a matrix to be inverted, it needs to be square. It's not square. How do I make it square? Well, look, this is called the expanded transformation matrix T. And we're going to start writing our stiffness matrices and transformation matrices in the expanded form. The expanded form says that if you have a bar element like this is node number 1, this is node number 2, and that's element 1. In the expanded form, an element has a local x-axis called x dash and a local y-axis called y dash. Now, we know that the local y dash means nothing, like this means nothing in trusses. We know that this y local means nothing in trusses, but at least for trusses, we need it for numerical reasons. Later in beams, we do need it because it's going to be the direction of shear. But in trusses, we're going to apply this only for mathematical reasons. So I expanded my matrix. It was CS00, and it was also 00CS. That was our T. And you had here U1 dash and U2 dash, and you had here U1, V1, U2, and V2. This was our old system, where I say the local equals the transformation multiplied by the global. But wait a minute, we want to expand this to become a square matrix. So I am going to add a movement in the local y-axis at node number 1 and a movement at the local y-axis in node number 2. And of course, V, based on a previous explanation, is negative sine cosine, 0, 0, and this is 0, 0, negative sine cosine. Okay? Once again, you might need to listen to this transformation matrix stuff multiple times and basically check out Dario L. Logan's book to understand this fully. I can use this to find the displacement and the forces in the global form. But wait, once again, I said before, a truss doesn't care about the forces or displacement in the direction perpendicular to the bar. Like if you have a bar here, in the perpendicular local y, the movement here doesn't affect anything in the truss. So how do we deal with this? Well, it's actually very simple. This is basically the idea. But of course, you might think, wait, this is too fast. So allow me to explain. Previously, it was F1x and F2x equals AE over L, and then a big matrix with 1, minus 1, minus 1, and 1. And it was multiplied by U1 local and U2 local. This was our old matrix. Now I want to expand it to be 4 by 4 stiffness matrix. So how do I expand this? I will add a force in the first point in the y, and a force for the second point in the y. This is local. And I will add here a movement local in the y and a movement local in the y. I would say, wait a minute, you said before that nobody cares about the force perpendicular to the bar because it's truss member. And the answer is yes, nobody cares about this. And that's why we're going to fill this with zeros and fill this with zeros, basically. What does this mean? What does the action of filling zeros give you? Try calculate F1y in the local. I said before nobody cares about this, so let's take a look if it's actually the case. You can see F-1y or something equals 0 multiplied by U1, 0 multiplied by V1, 0 multiplied by U2, and 0 multiplied by V2. So actually F1y equals 0 as it should be, because there is nothing that the truss feels in its local y-axis. That's 100% correct. For example, let's take a look on F1x. F1x equals, well, 1 multiplied by U1, minus 1 multiplied by U2, that's the old definition, plus 0 multiplied by V1, because nobody cares about the perpendicular movement in the local y, plus 0 multiplied by V2, because once again, nobody cares about the movement in the local y-axis. So this is only a mathematical manipulation to prepare your T matrix, your transformation matrix, for inversion. because we could not find k equals t star inverse multiplied by k local and t. Why couldn't we do this? Because there was no way to invert a non-square array. You cannot invert a 4 by 2 array or 2 by 4. So we needed to define a 4 by 4 matrix to be able to invert it. And this is exactly what we're going to do. Our local force equals our local stiffness multiplied by our local displacement. Now our local force is transformation global, and our local displacement is transformation global, which means that now I can invert my t, or left multiply, because it's a square matrix. And if you invert it, you get this thing that actually will give you k global. But you can see a little cheeky trick here. It was inverse and now it's transpose. So we are saying that the transpose of the transformation matrix equals the inverse transformation matrix. But why? This, of course, is something you should check out in Daryl Al-Logan's book. He refers to you to a proof for this, so you should double check that. For now, take me for my word, the transformation matrix transpose is the inverse. All right, so I know this might be too much theoretical blast, but wait, there is a cool example in the end, but we need to wait a little bit. So in the end, our global stiffness matrix is T transpose local T. And this is always the case, most probably the case, regardless of what the element is. If it's a beam element, if it's a truss element, if it is a shell element, the global stiffness matrix for an element equals the transformation transpose, stiffness, transformation. This transformation is for the displacement, and this transformation transpose was for the force. Does something cool for you. He prepares for you the global stiffness matrix directly. So what he is doing is, he is basically multiplying everything. He prepares for you this. You see this big multiplication? The book, Daryl Al-Logan, actually does that for you and gives you a ready-to-use global stiffness matrix for any truss element you face. And this is what you should once again add to your database of stiffness matrices. Stress calculations, because in the end you might be interested in calculating the stress inside the elements. Now, the book does give you a quick equation for this. I don't like it, to be honest. Now, I love the book, don't get me wrong. What I would be doing is, well, find the local force from your stiffness matrix and so on, and then basically divide by A. That's all you should do. So, I don't know, if you want to use this equation, be my guest. If you want to find the local forces and then divide by the area, be my guest. Of course, the stress is force over area. This is fitting. Now, one important task. If you use Daryl Al-Logan's equation, then you will get immediately positive and negative based on the case of the stress, tension, or compression. If you use my method, then you have to decide if F dash is indeed tension or compression. And I've spoken about this in the spring video, in the second video, I guess, when I dove deep into the local forces. I will link it on the top right. Take a look at it. It might help you. Now, why does Dr. Logan do that? He is preparing a variable called C in most cases. This is like a material or stress matrix. It's going to be relevant later, so I will revisit this if needed. Okay, so we finished our theory part, finally. And now we are back to our juicy examples. So, what do we have here? We have a truss. The truss is indeterminate, as you can see. And there are three components, element number 1, 2, and 3. And you can see the nodes 1, 2, 1, 3, and 1, 4. And this is the global system of X and Y. You can see that element 3 is the same as the global system. Element 2 is not, and element 1 is not. So he gives you the elastic modulus, he gives the area, and wants you to find the movement at node 1 and the stress in each element. All right, so how do we do that? What we do is we need to find, of course, there are multiple steps for the finite element method, but I will start immediately at finding the local stiffness matrix K. Now, wait a minute. I know that I said that Dr. Logan gave you an amazing shortcut, this, which gives you the global stiffness matrix directly for an element, but I am kind of a slow play guy, so I will slow play it. I will only slow play it for one element because there are some ideas I want to cover, and then I will fast play it for the other elements. So slow playing it, element 1 is between node number 1 and 2. So element 1 connects node 1 to node 2. So that is its local axis. I can see and try to read your mind. Some of you are thinking, okay, why did you say it's from node 1 to 2? Why didn't you say it's from node 2 to 1, right? You can consider both. There is nothing in the question that tells you that it's from node 1 to 2. So why did you assume this and not assume this? What is your reason? So to say the truth, there is no reason. As a matter of fact, it doesn't matter if you assume this or assume this. I will prove this to you in this video. So anyway, K equals A multiplied by E over L, 10 feet by 12 because inch, 1 minus 1 minus 1, 1, which gives you this. This is local now. And this is not expanded, it's just local. We said that we need to expand our local system because this connects F1-X, F2-X with U1- and U2-. But we said we need to expand this into Y and X because you want our transformation matrix to be a 4 by 4 transformation matrix because you want to be able to invert it or transpose it. So that's the reason why I took this stiffness matrix and I expanded it. How did I expand it? Well, I added V1 and V2. Now V1 and V2 are going to be added as columns and as rows. So you can see here the second row full of zeros, the fourth row full of zeros, the second column full of zeros, and the fourth column full of zeros. Notice this is the slow way of solving because yes, I could have used this matrix all along and saved myself a lot of headache. But no, I'm slow playing it because I want to establish the procedure because this exact procedure is used not only in the truss element but in every element. Because in the future you will not get a generalistic equation that finds the global stiffness matrix. No, sometimes you have to do the step-by-step procedure yourself. And that's what I'm doing now. Well, remember, if you say element 1 is from 1 to 2, then your theta is 90, which means your cosine is 0 and your sine is 1. And you can see here cosine, sine, 0, 0, negative sine, cosine, 0, 0, 0, 0, cosine, sine, 0, 0, negative sine, cosine. This is this. You have your transformation matrix. You have your local stiffness matrix. You should be using a software like MATLAB or Octave because this is now matrix multiplication. You could do it by hand, but it takes a lot of time. So you should have access to MATLAB or Octave or any mathematical software in which you're going to say the global stiffness matrix of the element equals T transpose KT, and you can see me inputting this in MATLAB and getting this exact value. Now there's a good question that you might ask, like why do you slow play it? I slow play it because slow playing it is more programmer friendly. Trust me, I work on the software called Strado. It's a nightmare to program the finite element method. I might even make video lectures about this, but this is in the far future. So it's much easier to be programmer friendly because you want to program a subroutine or a function or a class that just multiplies this without asking questions. Give it a K, give it transformation matrix, it finds you the global. It doesn't matter if this is for a shell or a truss or a beam. You can use everything the same so far. So that's why I'm using this. It's more programmer friendly. Now, if you want to use Darrell and Logan's method, if you want to fast play it, you will use cosine square, cosine sine, and so on, and you get the exact same values as me. Notice that this is going to be 5 multiplied by 10 power 5, so you get the exact equivalent matrix. That's fantastic. Now we have slow played it one time. For the rest of the elements, I'm going to fast play it. But before I fast play it, I asked a question. I assumed my element to be going from 1 to 2. Now, does it make any difference if you say from 1 to 2 and from 2 to 1? The answer is that the global stiffness matrix will not care and you will get the same global stiffness matrix, so there is no change. And here is a proof for you. I'm gonna basically do it from 2 to 1 and all the changes are highlighted in red. So now I'm dealing with node 2 to 1 with theta equal 270. Because if you go from 2 to 1, you're going down. And as you all know, this is negative 90 or 270 in standard degrees. So if you do this, well, you get a different transformation matrix, as you can see here. And this is the local matrix, sorry. You will get a different local matrix because now you are saying from 2 to 1. So your first degrees of freedom are 2 and your second degrees of freedom are 1. It looks eerily similar, but it isn't. U1, V1, U2, V2, now it's vice versa. because we were saying from 1 to 2, now we are saying from 2 to 1, so those two replace each other, and that is what happened. Secondly, the transformation matrix changed because the cosine of 270 is 0 and the sine of 270 is -1, which means negative sign is actually +1 because negative by negative is positive. If you multiply this in Octave or MATLAB, you will get the exact same stiffness matrix. You would think, wait a minute, that's not exactly the same. No, it is the same. For example, this element is V1 with V1. If you go to V1 with V1, you see this element. It's different in sorting, but same in meaning. So that's that. With that being said, now I'm going to fast play it. So those are the elements 2, which is from 1 to 3 with theta equals 45, directly from login, cosine, sine, and so on. And then element 3, which is from 1 to 4 with 0. And if you have 0, it means it coincides with the global axis, and you can see the very similar pattern of 1 and -1. With that being said, it's time to assemble the stiffness matrix. So we have done this a million times, so I will fast pace it very quickly. Now, for those of you who are viewing this as their first video in this series, I highly recommend that you check out the playlist, which I will link on the top right, to start from the beginning, to be able to understand why I'm fast pacing it here and not going as slow as usual. I hope that you don't mind with this, because we have different aspects to cover, and I don't want my video to be hours long. So now, how many degrees of freedom do I have? I'm talking about 2D systems. So at 1, I have 2 degrees of freedom, movement in X and movement in Y, so U1 and V1. At 2, I have 2 degrees of freedom, U2, V2, 3, and 4. So in general, I have 8 degrees of freedom, 2 for each node. And now I have to start to fill them. So how do I do this? I've done this multiple times before. I select this element. This element has a column of U1 and a row of U1. So I go to my stiffness matrices and look which element has U1 row and column U1. This is basically an element with U1. This also has U1 with U1, so there is a half. And this one has U1 with U1, so there is a 1. So if you add them together, you get the value here. If you thought that the value should be 1.5, you are not correct. Why? Because you can see a square root 2 here. So you have to divide this by square root 2. It's just a mathematical manipulation. So you can see this here, 1.34. You can see the relevant parts being cycled. Similarly, V1 with U1. If you go V1 with U1, you can see it here, here, and here, and so on. You just have to fill it. Of course, I just show it to you one piece because I've filled it a million times. Now we have to solve it. How do we solve it? Well, this is our K capital now, because that's our global stiffness matrix. K capital is the summation of all K smalls without a dash. You cannot sum, because you have to use K dash to find K and then use it to assemble the stiffness matrix. So what do you know and what don't you know? You know that 0.2, 0.3, and 0.4 are pinned, which means they don't move. So 0, 0, 0, 0, 0, 0. You also know that the force at node number 1 is -10,000 in Y and nothing in X. So you have 0 in X and -1,000 in Y. Now how can you solve this? You have to basically start slashing this row, this row, this, and so on with the columns 3, 4, 5, 6, 7, 8. And that's exactly what happens here, because degrees of freedom were restrained, which leaves you with a 2 by 2 system of equations. You can see it here. From the system of equations, you can find the displacement U1 and the displacement V1. This means that point number 1 has moved in the X a positive value and in the Y a negative value. Okay, now that's the first part answered. The second part was he wanted to find the stiffness in each element. Now I'm going to once again slow play it and then fast play it. The slow playing method is you want sigma, right? So to get sigma in an element, you need the local force in the element. How can you find the local force in the element? You need the local stiffness matrix and multiply by the local displacements. And that's the reason why I calculated this, why I slow played it. I have not gone into Daryl and Logan's method of just using one piece like this. No, I actually slow played it for educational reasons. We have our global displacements. We have our local stiffness matrix for element number 1. So can we just multiply K dash with D? No, because this is global and this is local. We have to find the local displacements. How do I find the local displacements? I mean, look. I basically, first of all, select the displacements from the global that are related to element 1. Element 1 connects node number 1 with node number 2, so those are the relevant displacements to my element, which are those. So I take them and isolate them. Those are my global displacements for element number 1. Now you know that the local equals the global left multiplied by the transformation matrix. You have the global displacements, you can multiply by the transformation matrix to give you the local displacements. If you do that, you get this. So with that being said, you have the local displacements, you have the local stiffness matrix. If you multiply them together, you get the local forces. It's negative 7950 and positive 7950. So if you have an element from 1 to 2, negative means going to the left for point 1. Positive means going to the right for point 1, which means that the force is tension 7950. Now, if you have the force tension 7950, you can divide by the area. Sigma equals F divided by A, which is the force divided by the area, which gives you the stress. This is the slow-paced method of finding the stress. The fast-paced method is to use Daryl and Logan's method, which is basically one matrix multiplication, and you get the answer immediately in all elements. Notice that there is a slight difference between me and Dr. Logan's answer. The reason for this, I believe, is numerical approximation. So yeah, this ends an interesting example, and I highly recommend that you open or view this video multiple times just to get the hang of it, because you are going to be doing this a lot. So this is a very important introductory video. I might even have the next video be yet another example, just to cement this idea of global stiffness matrices and trusses and so on. So yeah, that's everything I wanted to talk about. Before I finish, I want to give a huge CEE-sized shout out to our dear channel members whose names are going to be showing up on the screen. I would like to thank them very much, because with their contribution to the channel, they actually support the channel and help us do the things we do. So I thank you from the bottom of my heart. And that's everything. Well, if you have enjoyed the video and it was beneficial for you, then please like, share, comment, and subscribe, especially subscribing, because it helps increase the reach of my channel. As per usual, this is the Civil Engineering Essentials channel, and we'll catch you in the next video.